Hello everyone, welcome back to RC Circuits. This is lecture number 8. So in previous lecture, we have discussed some examples of RC circuits where there was sudden change of capacitor voltage in the circuit, which was violating the actual behavior of the capacitor. So we will solve some more examples of the same kind where there will be a sudden change of voltage across the capacitor for first order circuits. So we were in the middle of solving this circuit. So here the circuit was given and we assumed that C1 is equal to C2 and R1 is equal to R2, and we have got the initial voltage and final voltage is same for this circuit. So we'll quickly go through the circuit. So if you find the time constant of the circuit, since all parameters or all components are in parallel, so you will get a time constant as C1 plus C2 times, which is C equivalent, times R1 R2 by R1 plus R2, which is R equivalent. So this is finite, and since these two capacitors are in parallel and equivalently you can say this is a single capacitor of C1 plus C2, so this is a first order RC circuit. And if you find at t is equal to 0 plus, we got Vc1 is equal to Vc2 is equal to 2.5 volt. And also at steady state, since the capacitor will be open circuited, both the capacitor will be open circuited, you will get 5 times of 1 by 2, which is 2.5 for both Vc1 and Vc2. So initial voltage and final voltage are same for both the capacitors, which is 2.5 volt. But we are saying, since the time constant is finite, there should be exponential behavior of the circuit, right? But here we are getting both values as 2.5, initial and final. So it means for Vc1, and for Vc2, with respect to time, so assuming initial voltage is 0 for both the capacitors, so it was 0 and 5 volt is applied for t greater than 0, and then suddenly the capacitor will go to 2.5 since the initial voltages are 2.5, and then it will stay at 2.5 because the final voltage is also 2.5. This should happen because how can it go to from 2.5 to final voltage also 2.5? Let's say initial is 2.5 and final voltage is 2.5, the steady state. So if there should be exponential behavior for this circuit at this condition, then suppose if it should increase exponentially, then it should decrease again exponentially. But the same time this should not happen for a single capacitor, right? For a first order circuit. So this is not true. It will always stay at 2.5. That is how this circuit will work at this condition, where C1 is equal to C2 and R1 is equal to R2. Okay, these graphs are for this condition, but when will the exponential behavior happen in the circuit? So for that, maybe let's generalize the circuit by taking C1 and C2 are different values and R1 and R2 are different. Then we will solve the circuit for those parameters, and then let's decide at what condition it will go to exponential behavior or it will discharge or charge. So let's check that. So I will, or we can write here. So for t is equal to 0 plus, since both the capacitors are short circuited because of initial voltage of 0 volt, you will get impulse current. Since there is impulse current, you will get sudden change of capacitor voltage. So without assuming C1 is equal to C2, you will get Vc1 is equal to 5 C2 by C1 plus C2. Similarly, Vc2 is equal to 5C1 by C1 plus C2, since these two are in series and you are applying 5 volt. So these you will get initial voltages, and at steady state, without assuming R1 is equal to R2, then you will get Vc1 is equal to 5R1 by R1 plus R2, and Vc2 is equal to 5R2 by R1 plus R2. So now if you find general expression of Vc1, Vc1 is equal to final value. So if you remember, general expression of Vc of t is equal to, for a first order, final value plus initial value minus final value into e power minus t by tau. This is only for first order circuit. So if you find Vc1 of t, then final value is 5R1 by R1 plus R2 plus initial value minus final value times e power minus t by tau u of t. Since the transient is happening at t is equal to 0, so we have written this expression for t greater than 0. Similarly, Vc2 is final value plus or let's modify this equation. So if you solve this one, 5R1 by R1 plus R2 plus, if you take out 5, then C2R1 plus C2R2 minus C1R1 minus C2R1 by C1 plus C2 times R1 plus R2 times u of t. So C2R1 C2R1 will get cancel out. You will get 5R1 by R1 plus R2 plus 5 times R2 C2 minus R1 C1 by R1 plus R2 times C1 plus C2 times u of t. So this is final value and this is initial value minus final value. So if initial value minus final value is positive, suppose, then initial value should be greater than final value. It means this should behave like this. It means the capacitor is discharging. So I'll write down here. If initial value minus final value is positive, that implies capacitor will discharge. Similarly, if initial value minus final value is negative, it means the final value is more, initial value is less compared to final value. So the capacitor should have been charged. So capacitor will charge for this condition. So from this expression, if R2C2 is greater than R1C1, it means this is positive, initial value is higher. So this is for C1, right? So C1 will discharge. Similarly, if R2C2 is less than R1C1, C1 will charge, and suppose if R1C1 is equal to R2C2, then this term will be 0. So you will get 5R1 by R1 plus R2 times U of t. So it is just a step function. So there is no charging and discharging. It is only, it will go to some voltage and it will stay there. So if R2C2 is equal to R1C1, then C1 will stay at some voltage, or you can say C1 will be constant, no charging or discharging. So this is for VC1. What about VC2? VC2 of t is final value since it is across R2, so final value will get 5R2 by R1 plus R2 plus initial value minus final value times e power minus t by tau u of t. So if you solve this expression, plus 5 times here R1C1 minus R2C1, sorry, R1C1 plus R2C1 minus R2C1 minus R2C2. So the two terms of R1 R2C1 will get cancelled out, so you will get R1C1 minus R2C2 by C1 plus C2 times R1 plus R2 into e power minus t by tau u of t. So for the capacitor C2, for the capacitor C2, if R2C2 is greater than R1C1, it means this term will be negative, right? So if this term is negative, initial value is less and final value is more. So the capacitor C2 will charge. So the capacitor C2 will charge. And similarly, if R2C2 is less than R1C1, C2 will discharge. And if R1C1 is equal to R2C2, then there will be no charging and discharging for C1. It will stay at that condition. So we have taken C1 is equal to C2 and R1 is equal to R2, right? So if you multiply R1C1 and R2C2, then you will get this condition, right? R1C1 is equal to R2C2. So C1 will be constant and C2 will be constant. So that is what we have got, which is 2.5. It is staying at 2.5. So this is a unit step function. And if you find currents of C1 and through C1 and C2, then so IC1 with respect to t, since it is changing suddenly, there should be impulse current flowing through C1. So since it is changing from 0 to some positive value, there should be a positive impulse function with amplitude of C1 times this change in voltage, which is 2.5. Similarly, IC2 is also an impulse function because Vc2 is changing from 0 to 2.5. So which is again a positive impulse function, and this amplitude should be the corresponding capacitor C2 times the change in magnitude, which is 2.5. So these are the currents through capacitors for that particular condition. Now if you draw, let's take some condition. So R2C2 is greater than R1C1. Then if you draw Vc1 and Vc2 with respect to time, so if R2C2 is greater than R1C1, then C2 will charge and C1 will discharge, right? So C1 will discharge to some value and C2 will charge to some value. So the final value is 5 R2 by R1 plus R2, and here final value is 5 R1 by R1 plus R2, and initial value is 5 C2 by C1 plus C2, and this is 5 C1 by C1 plus C2. So this will discharge in 5 time constants. Similarly, this will charge in 5 time constants. Or we can't say this is exactly 5 time constants because this is not discharging from some initial voltage to 0, and this is not charging from 0 to some other voltage, right? So we derived 5 time constant is when it is discharging from some initial voltage to 0 and it is charging from initial voltage of 0 to some other final voltage. So this we cannot say, and yeah. If you draw IC1 and IC2, yeah, since C1 is changing from 0 to some voltage, you will get an impulse current in positive direction. So there should be impulse current in positive polarity should flow through C1, then only you will get sudden change from 0 to some voltage. And here also same. So this amplitude should be C1 times the change in voltage. Change in voltage is 0 to 5C2 by C1 plus C2, which is positive. So 5C2 by C1 plus C2. So this amplitude is 5C1C2 by C1 plus C2. Similarly, there should be impulse current through C2 in positive direction because it is changing from 0 to some positive voltage. So this amplitude is 5 times the change in magnitude. So 5C2 by 5C1C2 by C1 plus C2. And since C1 is discharging, there should be current flowing out of the capacitor C1. It means it is negative and it is going to some steady state value, which means the current through C1 should be 0 at steady state. So this amplitude of IC1 should be negative and this should go to 0. Similarly, since C2 is charging, there should be current flowing into the capacitor, which means IC2 is positive. But eventually, since steady state value is some constant, so IC2 should go to 0 from some initial voltage. So this is impulse amplitude or area. This represents the area, and so this initial value is, and if you want to find this initial value, so the general expression is final value plus initial minus final times e power minus t by tau, right? So if you want to find IC, which is C times dV by dt, right? So if you differentiate this constant, then you will get 0. Then the remaining is initial value minus final value by, if you differentiate this one, then you will get by minus tau times C, the capacitance, because IC is equal to C into dV by dt. So I'm just trying to find the initial current of this, initial magnitude of this current. So if you put t is equal to 0, then you will get C into initial value minus final value by minus time constant. So I'm just saying, from this we can say initial magnitude of current is equal to minus initial value by minus final value by time constant times the corresponding capacitor. So this should be C1 times initial voltage minus final voltage is, so 5C2 by C1 plus C2 minus 5R1 by R1 plus R2. And this should be minus times 1 by tau. So if you solve this, you will get this magnitude. Similarly, you can find this magnitude also. So I'm just writing for now. So it should be C2 times C2 by tau times final value minus initial value. So 5R2 by R1 plus R2 minus 5C1 by C1 plus C2. So this is how you will get this initial magnitude also. And finally the current goes to 0 at steady state. Yeah. So similarly you can find for other condition also. What if R1C2 R1C1 is greater than R2C2, and if R1C1 is equal to R2C2, then it will go to some voltage and it will stay there. So you will get a unit step function for both the capacitor voltages, and you will get impulse current for both the currents. So this is about that circuit, and we will solve some more circuits. So here you are pumping a constant current. So since these two are in series, it doesn't matter whatever the impedance here, you are directly pumping a constant current of 5 amps through this capacitor, right? So if you pump a constant current through a capacitor, then there should be linear charge across the capacitor voltage. So since you are pumping at t greater than 0, for t is equal to 0, the switch is closed, so you will get a linear function for Vc of t. And this slope is I naught by c, right? So which is 5 by c. So how did you get that? Because v is equal to 1 by c integral I dt. So this we have already discussed. Since IC of t is constant, you will take out that constant. I am assuming it is I naught, and integral dt. Integral dt is t. So I naught by c times t. So this is the slope. This is in the form of y is equal to mx. So m is the slope and x is the time. So, and suppose if you want to find the time constant of the circuit, then for t greater than 0, since you have constant current source, just open circuit this current source and you will get c times the impedance across the capacitor terminals, which is infinite. So since the time constant is infinite, this will not go to stable value, so it will keep on charging ideally. So this will go eventually. And for this circuit, yeah, so for this circuit, so these two circuits are different. Here you are directly pumping a constant current through a capacitor, but here you are not. And here also time constant is infinite, but if you find the time constant here, then open circuit this one, then you will have a finite resistor across the capacitor terminals, which is C times those two resistors are in series. You will get 2 RC as time constant. So since it is first order and time constant is positive, you will get exponential behavior. But here not. So if you find initial value at t is equal to 0 plus, short circuit the capacitor, then you will get some finite current through the capacitor, right? So if you are pumping some finite current through a capacitor, then the capacitor will not change its voltage suddenly. Only when there is some impulse current through it, then only the capacitor voltage will change suddenly. So let's say this is IC of 0, you will get 5 by 2, 2.5 amps. And for t tends to infinity, at steady state, the capacitor will be open circuited. So you will get the voltage as 5 times of R. This is 5 amps and this is R. You will get voltage of 5 R across the capacitor terminals. So this is Vc of infinity is 5 R. So you will get exponential charge from 0 to 5 R. and this is in 5 time constant, which is 10 RC. And the final value is 5R. So if you write the expression, then final value into 1 minus e power minus t by tau times u of t. And since the capacitor is charging exponentially, you will get a positive current with exponential decay. So how can you find this initial magnitude? Initial magnitude is final value minus initial value by time constant into c, right? So final value minus initial value is 5R into c by time constant is 2RC. So yeah, which is 2.5 amps. So I'm just trying to derive from that from this formula just to confirm, because we have already got initial current of 2.5 amps, right? So this is correct. So it is going from 2.5 amps to 0. Yeah. So this is the difference between these two circuits. Here we are directly pumping a constant current through a capacitor, but here the capacitor charging should be exponential, because we are not pumping a constant current through this capacitor. So that is the difference between these two circuits. So if you look at the circuit, you have two capacitors, and one capacitor is initially charged at 5 volt, and here it is not given. So assume it is initially this there is no initial voltage across the capacitor. So we will first solve this circuit. So at t is equal to 0 plus, the capacitor should be represented with its initial voltage. So this is 0 and one is 5 volt. So 5 volt and 0 volt. So you will get infinite current through the capacitor. It means sudden change of voltage. Since that current is flowing in both the capacitors, so there should be sudden change of voltage across both the capacitors for both C1 and C2. So if you want to find the initial voltage, then these two capacitors should be represented with the same but with less impedance, because at t is equal to 0 it is saying very high frequency. So at high frequency the capacitor impedance should be low. So this is lower impedance, and C1 C2. So actually the capacitor C1 should be across these two terminals completely. This is VC1 and this is VC2. Because so this 5 volt is the initial voltage across the capacitor. We just take out that 5 volt and represent the capacitor separately. So this is for circuit analysis, but ideally combinedly these two form a original capacitor with initial voltage of 5 volt. So this is Vc1, this is Vc2. So since these two are in parallel, Vc1 is equal to Vc2. So Vc1 should be is equal to Vc2. This is only at t is equal to 0 plus. So Vc2 is, since two capacitors are in series, so I'm assuming it has no initial voltage and this is also no initial voltage. I'm just taking out the initial voltage from that capacitor C1. So with the battery of 5 volt, you have two capacitors C1 and C2 are in series. So you will get Vc2 is equal to 5 times C1 by C1 plus C2. If you find the voltage across this capacitor separately, then you will get 5 times C2 by C1 plus C2. But you want, so combinedly this is the complete capacitor, right? So if you find Vc1, then you will get 5 times of C1 by C1 plus C2. So this is also Vc1. So the initial voltage of both the capacitors will be same. Now if you find that t tends to infinity at steady state, both the capacitors will be open, right? So take out the initial voltage and open circuit the both the capacitors. So here also this is Vc1 and this is Vc2. So since both are open circuit, I can assume these two capacitors with high impedance. So this is with high impedance at steady state. So Vc1 is equal to Vc2 is equal to 5 times C1 by C1 plus C2. So it means there is no charging and discharging, I mean exponential charging and discharging for the both the capacitors. So Vc1 Vc2, initially Vc1 is 5 volt, right? And both are going to 5C1 by C1 plus C2, and at steady state also it is same. So it should be 5C1 by C1 plus C2, and initial voltage for C2 is 0 and it is going to 5C1 by C1 plus C2. Yeah, this is how this concept of switching capacitors will work. So if you draw IC1 and IC2, then both should look same but with opposite magnitude. So since for t less than 0 the voltage is constant, so you will get dv by dt is 0. So IC1 is 0 and it is going from 5 volt to 5C1 by C1 plus C2. So from higher to lower, so you will get a negative impulse current with magnitude of C1 times the change in voltage, which is 5 minus 5C1 by C1 plus C2. So you will get, actually this should be minus, because or if you do it plus and you reverse these two terms, then you will get negative value. So minus C1 times 5 C1 5 C1, and you will get 5 C2 by C1 plus C2. And for IC2, initially it was 0, and for t greater than 0 also it is 0 because it is constant, but only at t is equal to 0 you will get impulse current with magnitude of C2 times this change in voltage, 5 C1 by C1 plus C2. So both the impulse magnitudes are same, which is 5 C1 by C1 plus C2, but one is in opposite direction and one is in positive impulse. So yeah, and that is how that circuit will work, and we'll check this circuit. So okay, so for the previous circuit we assumed initial voltage of C1 is 5 volt and initial voltage of C2 is 0 volt. Suppose if you have some initial voltage of for both the capacitors C1 and C2, so we will solve for that and we'll go to the circuit next. So if V1 and V2, okay, I have already this question. So if you have V1 and V2 of initial voltages across both the capacitors, then at t is equal to 0 plus, you will represent with both with initial voltages, right? So this is V1 and this is V2. So you can equivalently represent with a single voltage source with 0 resistance. So we'll get impulse current in either direction. So I'm taking only in one direction, so you will get some impulse current. So there will be sudden change of voltage, and you will represent both the capacitors with lower impedances, and you have, so this is VC1 and this is VC2. So C1, C2, V1, V2. So if you find the voltage across these terminals, you will get initial voltage of VC1 and VC2 for t is equal to 0 plus. So since V1 is in this polarity and negative of this is connected to negative of V2, so these two will be subtracted, right? If uh, if opposite polarities of both the batteries are connected, then those two batteries will be added, and if both the capacitors of same polarities are connected, then these two will be subtracted, and whichever is the higher voltage you will get at that polarity. So I'm assuming, suppose if V1 is greater than V2, then you will get V1 minus V2 in this polarity. So equivalently you have a battery of V1 minus V2 and two capacitors are in series. So across this particular capacitor C1 you will get, so I'm directly write the equivalent of this total capacitor C1, VC1 is equal to Vc2 is equal to V1 minus V2 times C2 by C1 plus C2 plus V1. So you have V1, and if you want to find the total voltage, then add this V1 to this voltage, right? So this voltage we got this expression, which is V1 minus V2 into C2 by C1 plus C2, and you are adding V1 to it. So you will get V1 C2 minus V2 C2 by C1 plus C2 plus V1. So you will get plus V1 C1 plus V1 C2. Actually, so we are considering V1 minus V2 as equivalent voltage, right? So if V1 minus V2 is equivalent voltage and you have both the capacitors, since this is in this polarity, if you find the voltage, then you will get in this polarity, right? So because it will charge in this direction, it means you will get this voltage V1 minus V2 into C2 by C1 plus C2 across this capacitor in this polarity. So you will get in this polarity, but Vc1 is in this polarity, right? I mean, if you want to add these two, then take this polarity of voltage and this V1. So this polarity and this polarity are in opposite direction. So if you understand that, it's good. So that you will get minus here. So this is minus and this is plus. These two will get cancelled out. So you will get C1 V1 plus C2 V2 by C1 plus C2, which is Vc1 is equal to Vc2 for t greater than 0. Similarly, for t tends to infinity also, the circuit remains same, but these two capacitors were having very low impedance. Now at t tends to infinity, they will have very high impedance because of, for our circuit analysis. So you will get both the capacitors are open and the same voltages. So if you replace those two capacitors with high impedances, so these two are high impedance, then you will get the same expression. So here I have solved for Vc1, you can solve for Vc2 also. So equivalently you can take V1 minus V2 of this voltage and you will find this capacitor voltage, which is V1 minus V2 into C1 by C1 plus C2, and then add this voltage V2. Then you will get the same expression C1 V1 plus C2 V2 by C1 plus C2. This is one way of solving. So you will get same voltage for both t is equal to 0 plus and t tends to infinity, which means whatever the initial voltage across both the capacitors, let's say this has V1 and the capacitor C2 has V2, right? So it has V2. Let's say it is some other voltage. Now finally both the capacitors will go to the same voltage, which is C1 V1 plus C2 V2 by C1 plus C2. This is the final voltage. This is also V infinity. So both the capacitors will go to the same voltage. So that is how the charge sharing will happen in this circuit. So the same circuit you can also solve by using the charge conservation. So if you see, this circuit has initial voltage of V1 and V2 for t less than 0, right? So for any circuit, the charge conservation should follow, right? So the total initial charge is, so Q is equal to CV. So for C1 you will get C1 V1, and for C2 you will get C2 V2. So this is the initial charge. What is final charge? Both the capacitors will go to same voltage, right? So that same voltage I am assuming V of infinity. So you will get for C1 into V of infinity, and for C2 also should be V of infinity into C2. This is the final charge. So if you solve this one, you will get V of infinity is equal to C1 V1 plus C2 V2 by C1 plus C2. So this is how you will get the final voltage across both the capacitors. Yeah. Now we will solve this circuit. So both the capacitors are having initial voltages of V1 and V2, and we are applying some voltage source at t is equal to 0. So at t is equal to 0 plus, you have V and V1 and V2, and you don't have any resistor, so you will get impulse current through the capacitors. So if you want to find the initial voltage or final voltage, so the circuit analysis, for circuit analysis, the circuit remains same for both initial and final steady state circuits, right? So this is V2 and this is C2. So this is for t is equal to 0 plus, and this is also same as t tends to infinity also, because both the capacitors will be open circuited, and if you want to find, you will replace that open circuit with high impedance of capacitors. So the circuit looks like same for both. So this is VC1 because we have taken out the initial voltage, and this is VC2, and this is V2, and this is V1. This, let me see here. So this is V1 and V2 are initial voltages, and V is the source that you have applied. Now find VC1. So this positive terminal is connected to this positive terminal, and this negative terminal is connected to this positive terminal. So these two capacitors will add up, and these two capacitors, I mean this capacitor, sorry, these two voltages will be add up, and this source voltage will be subtracted with this equivalent voltage source or equivalent voltages. So V1 and V2 will add up, and V with V1 and V2 you will subtract, because opposite polarities are, I mean same polarities are connected. So if you assume the voltage source is greater than this V1 plus V2, then you will get that circuit with the polarity of the voltage source because it is bigger compared to these two. So V minus V1 plus V2. So this is for circuit analysis only. So this is the equivalent voltage source and you have two capacitors. So if you find, you will get these two voltages, but if you want VC1, then it is across the total these two terminals. So VC1 is add V1, then this voltage is from here, you will get V minus V1 minus V2 times, so this is C1 C2 times C2 by C1 plus C2. That's it. And if you want to find VC2, then add this V2 first and find this voltage. So this voltage is this voltage. So V minus V1 minus V2 times C1 by C1 plus C2. That's it. So this is at t is equal to 0 plus and for t tends to infinity also. So you will get unit step functions for both, not unit step functions. You will get a constant voltage for t greater than 0 for both the capacitors C1 and C2. So we can draw that. This yeah. So you can solve this expression also, but that's we are not going to solve now. So if you draw VC1, then you have initial voltage of V1 and it is going to some final voltage. Now the final voltages are different for both the capacitors, but if you look at the previous circuit, then you will get you don't have any external voltage source, right? So if you just connect the both the capacitors with any initial voltage, then you will get final voltage of same voltage, but not in this case. If you connect with some external voltage, you may get some different voltages. It depends on the capacitors and initial voltages. So this is V1 and this is VC1 of infinity. So this is VC1 of infinity and this is VC2 of infinity. So whatever the initial voltage, let's say some initial voltage of V2, I don't know, it can go higher or lower, it depends on the values. So you will get VC2 of infinity. So depends on these two, you will get some impulse currents. So for both the currents, t less than 0 the currents are 0, and for t greater than 0 also the currents are 0, because for t greater than 0 both the capacitors are having constant voltage. So IC1 of t and IC2 of t 0 for both t less than 0 and t greater than 0. But IC1 of t and IC2 of t are having impulse current at t is equal to 0. So this is about this circuit. Yeah. So we'll quickly solve the circuit. So the circuit is given and you have two capacitors, and for t greater than 0, you will get this circuit, right? C1 and C2. So since C1 and C2 are in parallel, you will get time constant as C1 plus C2 times R. So this is finite and this is first order, so you will get some exponential behavior. So if you find that t is equal to 0 plus, then this should be represented with initial voltage of 5 volt, and you have a resistor, and this is 0, and time constant is finite, and this is first order. You will get exponential behavior. So since this is short circuited across the voltage source, you will get impulse current. If you have impulse current, of course there should be sudden change of voltage. So if you want to find that voltage, then represent the capacitor with lower impedance. So this is C1, this is 5 volt, and this is R. So if you have a lower impedance across a finite impedance, so this is lower, so equivalently you can ignore that finite impedance, and you will, this is approximately short circuited, and you have some impedance across this short circuit, so you can neglect this one. So this we have already discussed. So we will get 5 volt, C1, C2 and 5 volt. So this is both VC1 and VC2 for t is equal to 0 plus. So VC1 of 0 plus is equal to VC2 of 0 plus, and the steady state voltages might be different because there is some finite time constant and it should behave as exponential behavior. So let's check at t tends to infinity, but for t is equal to 0 plus, this is 5 times C1 by C2, C1 by C1 plus C2. So for t tends to infinity, which is at steady state, so this will be open circuited and you have a finite resistor. So this is 5 volt, and this capacitor will be open circuited, and this should be open circuited. So there is 0 amps of current is flowing through this finite resistor, so you will get voltage drop of 0. So if voltage drop is 0, then you will get across capacitor C2 and C1 0 volt, which means finally both capacitors are going to 0 volt. So the steady state voltage of both the capacitors, Vc1 of infinity and Vc2 of infinity, is 0 volt. So if you draw Vc1 and Vc2, then initially Vc1 is having 5 volt, and at t is equal to 0 plus, and initially Vc2 is 0 volt, right? So this is 0, and both are going to the same value. So this is 5C1 by C1 plus C2, and 5C1 by C1 plus C2. So this is going from 0 to this value, and this is going down from 5 to this value, and exponentially those two are reaching to 0 at steady state. That's it. So can also draw IC1 and IC2. Since at t is equal to 0, there is sudden change of voltage, you will get an impulse current of IC1 at t is equal to 0. So there is some impulse behavior at t is equal to 0, and the magnitude is minus C1 times 5 minus 5C1 by C1 plus C2. C1 times this change in voltage, and since this capacitor is discharging, you will get negative current through capacitor C1, and it is going to 0. So this magnitude also you can find. So this amplitude and this magnitude should be different, and for IC2, since it is going from 0 to some voltage, you will get a positive impulse function for IC2. So there is some positive impulse current through capacitor C2 with magnitude of C2 times 5C1 by C1 plus C2. But C2 is also discharging. It means IC2 should be negative, and it should be exponential, and it should go to 0. So you will get some magnitude. So this is C2 times initial value minus final value by time constant, right? So if you find that, you will get, so this is minus C2 times 5C1 by C1 plus C2 into 1 by time constant, and similarly this is minus C1 times 5C1 by C1 plus C2 into 1 by tau. Yeah, these two correct. Yeah, that is about for today, and we will discuss some more complex problems in upcoming lectures. So the main mode of this course is forget about the expressions. So the expressions, writing the expressions is secondary. Intuitively you could able to draw the waveforms for voltage across the capacitors and current through the inductors, and vice versa. So drawing the voltage and current through the capacitors and inductors is important for this course. So that is for this lecture, and if you like this explanation, please share to your friends, and if you have any doubts, please comment down. Yeah, thank you.